Today we're going to pick up where we left off last class, and we're going to, just quickly review Gram-Schmidt, and then I'm going to introduce the fundamental theorem of linear algebra. This is different from the fundamental theorem of algebra, which is that if you have an nth degree polynomial, it must have n roots. This is the fundamental theorem of linear algebra, which many of you have likely seen before. And then we'll talk about an optimization problem related to this fundamental theorem. Then again, we'll do a little bit of review where we'll talk about symmetric matrices and the spectral theorem and their properties. And then we'll come back to, again, an optimization problem related to symmetric matrices, which is the variational characterization. Quick admin announcements is that we know that some of the discussions were very full. So please note that Wednesday, Thursday, and Friday in a given week all have the same material. Feel free to go to any section. We're looking into slightly larger classrooms in case you were one in a section that was completely overfull. There is no section in Moffitt. All of the sections are in 540 Corey. Do not pay any attention to what section you're enrolled in B courses or whatever thing you officially enrolled in. Go to any section you want. Follow the information on the course calendar. So don't follow anything in B courses or whatever you were officially enrolled in. That's not relevant to us. Whatever is on the course website is what you should be doing. Okay? So hopefully, if there was anyone who had any confusions about discussion, you'll figure it out. Okay. So just a quick clarification on Gram-Schmidt that we talked about last time and the QR decomposition. I'm not going to go over it again, but I made a small typo last time that one of your colleagues thankfully pointed out. What the Gram-Schmidt or QR decomposition allows us to do is write A as the product of Q and R, where Q is orthonormal and R is upper triangular. So I mistakenly wrote R as diagonal, even though I drew out an upper triangular matrix. I wrote it out as diagonal, so thank you for pointing my typo out. I really appreciate it. But anyone who wrote down that R is diagonal in their notes yesterday, I meant upper triangular. So please make that clarification, okay? I'm not really going to go into much more detail on this. So Gram-Schmidt is basically the procedure that we talked about last time, and hopefully we'll get to apply it in an interesting scenario in class later today. Okay? So with that, I'm going to move to the fundamental theorem of linear algebra. And this is a tool that is useful for understanding, in general, vectors and vector spaces in the context of what happens to them under matrix transformation. So remember, matrices are operators that allow us to transform one vector space into another, right? And this is incredibly valuable for thinking about changing of representation. So for example, in the work that I do in control theory, you're often thinking about different perspectives on the states of a particular system. So for example, if you have a car and the states of your system are your position, your velocity, your acceleration, maybe your momentum, you could also think about it in transformed coordinates. So for example, sometimes you think about a reference frame which is tied to Earth, or you might think about things in a frame that is actually attached to the object itself. So there might be two different coordinate systems that you're trying to transform between. Matrix multiplication, or matrices in general, can help you transform between these different kinds of spaces. And looking at things in different vector spaces can help you understand a lot of the properties of vectors. And we'll do this throughout the class. But what we're doing right now is building out a tool that will allow us to do this easily and fluently. Okay? So what this fundamental theorem of linear algebra says is it says that if I can take Rn, the vector space, I can decompose Rn into one vector space, which is represented by the null space of a matrix A. And for clarity, let me say A is Rm by n, plus, and this notation is called the direct sum the range space of A transpose. And this is equal to Rn. So what this is saying, that any vector in Rn, I can write it as the sum of one component that belongs to the null space of A and another component that belongs to the range space of A transpose. Now, quick note to yourself. Would it be okay to write range space of A here? What would happen? What would happen if I wrote range space of A here? Dimensions are wrong, right? So remember, A is, let's say, m by n. So any vector x that A is multiplying has to be an n by 1 vector, right? It has to belong to Rn. So the null space is n-dimensional, but the range space is going to be stuff that comes out on this side, right? And this is going to be an m-dimensional vector, right? So that's like one way to remember where the transposes are, is to think about the dimensions, right? The null space and the range space are different dimensional spaces, okay? So people get this tripped up. People are like, why is there a transpose here? We're going to prove why there's a transpose here, and it'll become clearer. But I want you to, it's important to note that the dimensions of these spaces are things that matter, right? And similarly, I can write, if I wanted to say something about the range space of A, well, I could say the range space of A, direct sum with the null space of A transpose gives me Rm, okay? We're only going to prove the first one because the second one follows immediately as a corollary simply by replacing A with A transpose, right? So we're only going to focus on proving this first thing. This is not good. Any questions? To prove this, we're going to make use of a tool, which is the orthogonal decomposition theorem. Oh, this is in the textbook. I wrote down the number. What was the number for this? This is theorem 3.1 in the textbook. ECG, I think that's how you're referring to it. 3.1. This is theorem 2.1, in case that's useful. So let X be any general vector space, and let S be a subspace. Then, for every vector X belonging to X, I can write X as the sum of some S belonging to S plus some R, where S belongs to S and R belongs to S perp. And what do I mean by S perp or S orthogonal? S orthogonal is that set of all vectors that are orthogonal to the vectors in S. So this is basically the set of all vectors R such that R inner product S is equal to 0 for every S belonging to S. Okay? So what this is saying is that if I take any subspace, so I have some vector space X, right? And I can take, let's say, some subspace S, then whatever remains that is not in S, I basically can denote by S perp. And every vector in X can be written as a sum where one component belongs to S and the other belongs to the orthogonal complement. And this is written as this direct sum. So basically X can be written as S direct sum with S perpendicular. Okay? Yes, question? Just sum for sets is not necessarily defined. We could define it, but here because we're defining, like, what do you mean by sum of a set? We have to define an addition operation on sets, right? Addition operations on set could be unions. They could be, like, there's a lot of ways to define addition on sets, right? So that's why we are defining a specific type of addition, which is different from the union, which is this direct sum, which is I'm saying that the direct sum of two vector spaces is saying I take one vector from the first vector space, the second vector from the second vector space, I add them, and all such resulting vectors are in the direct sum, which is related to the union but is distinct.
I think the difference between sum and direct sum in linear algebra is that direct sum, in this case, an element in S can be written uniquely as an element in S plus an element in S per.
Yep.
But sum is the representation is not unique.
Good point. Another point that was raised is that direct sum implies a uniqueness of decomposition, which is also what we're going to be using here. Okay? Other questions? Okay, so I don't know if we're going to have time to prove this. If we do, I'm going to try to save some time at the end of class to prove this theorem. If not, its proof is in the textbook. I encourage you to look at it. Hopefully we'll get some time to at least talk about the proof sketch of this. But what I want to do is I want to now use this to prove the fundamental theorem. So now, to prove basically that this is true using this theorem, what do I need to show? I need to basically show that the null space of A and the range space of A transpose are orthogonal complements, right? That when I take, the orthogonal complement of this, I get this. So I want to show that null space of A orthogonal complement is equal to the range space of A transpose. Everyone understand this step? Okay. So now this is a set equality, right? To prove a set equality, what do I need to do? How do I do something like that? Yeah. You're going to say the same thing? Yeah. People are saying you have to show that each set is a subset of the other, right? So we basically have to show that the null space of A is a subset of the range space of A transpose perpendicular, and the range space of A transpose perpendicular is a subset of null space of A. And I can write this on either side, right? So here, it's slightly easier to show it this way, so I can think of the orthogonal complement on being on either side of these. Because the orthogonal complement of the orthogonal complement returns the set itself. Okay, so does everyone see this subset relationship that we're trying to prove? Okay, so why don't you, start thinking about how you might want to prove the first one. Take a minute and try to do it by talking to your neighbor, talking to your friend. See how you might be able to do this while I erase these boards. So, how many people have any ideas? Anyone want to share an idea? Someone else hasn't spoken yet. Okay, we'll wait.
Choose an x that's in null space A.
Okay, choose an x that's in the null space of A. So what do we want to show? We want to show that the null space of A is contained inside the orthogonal complement of the range space of A transpose, right? So we say, let's consider an x in the null space, and we want to show for every such x, it had better belong to this other set as well, right? So if I know that x is in the null space of A, what does this tell me about x? This means I know that A times x is equal to 0, right? By the definition of null space. Okay? And what do I want to show? I want to show that x belongs to the range space of A transpose perpendicular. So now, if I had some W, so for all W, such that W is equal to A transpose times, let me match my notation, some Y. Right? What does it mean for W to belong to the range space of A transpose? Remember, if you're ever stuck writing a proof, what's the first thing and most important thing you do? Try to translate things into mathematical equations, right? So what does it mean for X to belong to this set? It means that, let me first write out what the range space of A transpose is. Well, that's all the W's that can be written as A transpose times some other vector, right? And now, if I'm orthogonal to all of these W's, then I'm caring about all of the X's. I want to show that, X, inner product with this W, what had this better be equal to? This had better be equal to 0, right? This is what I want to show, right? If X is in the null space, then for all W's of this type, this had better be equal to 0. Okay, so let's try computing it out, right? So let's consider X inner product W, which is equal to X inner product A transpose Y, which is equal to X transpose A transpose Y, right? So when I look at this quantity, what are the dimensions of this quantity? Is this a vector, a matrix? It's a scalar, right? What is X transpose? X, remember, belongs to Rn. So X is a vector like this. So X transpose is a 1 by n, right? So this is a 1 by n times an n by m times an m by 1. So this thing is a scalar. Right? Everyone see that? So I can just take the transpose of this, which gives me Y transpose AX. But what is this equal to now? 0. Feeling a chilling silence in the classroom. Okay, ask me a question. Are people lost or are people bored? That's the thing, I can't tell the difference. Okay, I heard one lost. Ask me a question. Yeah.
So you said you were allowed to take the transpose of it because you knew it was a scalar.
Good, great question. So what is a scalar, right? A scalar is some number, so aside. So a scalar is something like 2 or 3 or 8 or 10 million, something like that, right? So a scalar is basically a 1 by 1 matrix or a 1 by 1 vector, right? So when I take the transpose of a scalar, what do I get? Still a scalar, right? So basically, when I know that this is a scalar, I can take its transpose, and that gives me, that's why I'm allowed to do that. There's another way of seeing this. If I know that AX is equal to 0, I can take transposes of this equation. If I take transposes of this equation, this would tell me that X transpose A transpose is equal to 0, right? And then I could directly conclude from here that this inner product is 0 as well. Like there's multiple ways of finessing the math. Does everyone see that? So, good. So this is why I'm allowed to take the transpose. Yes, question?
Yeah, so I'm following with how you got from like the dot product of X and W all the way to like the Y transpose times A times X vector equals 0. So how exactly does showing that equality prove that it exists in the null space of?
So what I've shown is that if W can be written as A transpose Y, then X inner product with W must be 0, right? Which is what I exactly wanted to show, because I wanted to show for every W of this form, I wanted to show that x must be orthogonal to it, which is this 0, right? This is exactly what I wanted to show, and turns out to be true.
So that dot product constraint isn't.
This is not a constraint. This is what we want to show. This is what we want. This is not a constraint.
So that's not what you're starting off with?
No, we're starting off with this. This is what we're starting off with. This is what we want to show.
Okay, cool, got it.
Great. Yeah?
Okay, so do we have the assumption that we can use inner product in this space?
Yes, we're working in the reals. So we're working in real vector spaces. We're always going to assume inner product. In this class, we're not going to have spaces that are not inner product spaces. Okay, so this establishes one. Are we done yet? All we have shown is that this is a subset of this. Now we have to show the other way around, right? So any ideas on how to show the other direction? So let's start, right? Let's consider some x that belongs to the range space of A transpose perpendicular, right? So what does this tell us? What does this mean? This means that for every w such that w is equal to A transpose y, I have x inner product w is equal to 0, right? Now I'm starting with this. And now what do I want to show? I want to show that this x had also better be in the null space. Okay? So take a minute, talk to your neighbor from here on as to how to go. These two are different proofs. It's important you understand why this is different from this. If you think that, oh, it's just the same, it is not, and that's the reason I'm emphasizing it in lecture. So take a minute from here on out, try to complete the proof. Talk to your neighbors. Okay, how many people have some idea of how to proceed? How many people would like to take a collaborative hint? Group hint? Somehow. Okay, let's do it. So we have this x. So we know, this is what we know, right? What do we want to show? We want to show, this is not given to us, we want this, that x belongs to the null space, which means that ax is equal to 0, right? We want to show this. So here, if I expand this out, right, what do I get? This is equal to 0. This is also equal to x inner product A transpose y, which is equal to, again, I can write this as x transpose A transpose y, right? Again, this is a scalar. Again, I can take a transpose, so I have this as y transpose ax, and I know that this is equal to 0, right? There I wanted to prove it was equal to 0. Here it's given to me. So I have some vector times some other vector is equal to 0. Can I conclude that ax is 0 because I have some, x times y equal to 0? Does this mean anything? Does it mean that one of these has to be 0? For matrix vector multiplication, this is not true, right? That's what null spaces are, right? These are vectors that go to 0. So, ax could belong to the null space of y transpose. But what do we know here? What is key? Do we know that w is one specific vector equal to A transpose y? We know that this is true for every single w, right? That means that this is true for every single y. So I can write that this is true for every y. So now, if I have, I don't just have this one equation. I have multiple equations. I have an infinite number of equations that are saying that y transpose times ax is equal to 0. So now I can choose y to be anything. I could choose y to be, 1 and then a bunch of zeros. I can put 1s in every element. I can make this one by one pick out the elements of the vector ax, right? Because I have this true for every y, I can then conclude, since true for every y, I must have that ax is equal to 0. It's a subtle point, right? It's very tempting to want to conclude from here just directly, that, but we can't, right? We cannot conclude. Like, it doesn't work exactly the way the other direction did. Is the difference between the two sides clear to everyone? This is important. Yes? Questions? Yes? Okay. So let's think about it in the following setup. So let's say I give you some vector A times some B is equal to 0 for every vector A transpose. Okay? So now I have A looks something like this, B looks like this. Okay? So now let me first try, let's say so B is, let's say, B1, B2, all the way up to Bn. Okay? I can pick A to be 1, 0, 0, 0. What does this equal to? This gives me basically just B1 followed by zeros, right? But this is equal to the 0 vector. What does that imply about the first entry of B? It must be 0. Can I do this for the second entry and the third entry? Right? So because this is true for every A, I get the power to pick A. That's what I'm using here. Everyone with me? Yes, question. What if A is just all zeros? You're saying that, well, maybe, this was already true, that A was just all zeros. Right now, we're not taking any inverses of A anywhere, so it wouldn't actually break the proof. This would still be true. Because there's no inversions happening, right? We're never putting in a condition that A cannot be the 0 matrix. Still valid. The argument still holds. Yes, last question.
Could you just say that x is, so we know x is perpendicular to all rows of A, so then ax equals 0. Can you just say that? Like, if you take x and go
We don't know that. So the question is, can we say that x is perpendicular to all rows of A? We don't know that. That's what we need to prove.
But you said that it's in the range, or x is in the range is perpendicular to A transpose. Right, so we know.
Oh, sure. You can make an argument that way as well. This is essentially that argument written out in math. That's essentially exactly what this is. It's done more step by step. Okay. Good. So now we have this. Basically, these two things give us that 1 and 2 are true, which implies that the null space of A is the orthogonal complement of the range space. This, combined with this theorem, tells me that for every single vector in Rn, I can write it as some component in the null space of A plus some component in the range space of A transpose. Okay? Great. We are now going to use this to solve an important optimization problem. It's not as important as least squares, but it's in close competition. By the way, is the red better than the blue, or blue is still better? I can't understand what you said. Blue, okay. The minimum norm problem. Okay? So least squares helps us understand problems of the following sort. AX is equal to B when A is a tall matrix. AX equal to B. And so basically what I have here is an overdetermined system. Okay? I have lots of measurements. X is my unknown. I have lots of measurements about my unknown vector x, and there's more equations than I have unknowns. What about the case where A is a wide matrix? So I have A x is equal to B. So I have an underdetermined system. Here, the number of exact solutions in general is going to be 0, right? Because you have too many equations, you're not going to find a vector x that satisfies all of them. Here, when I have fewer equations than I have unknowns, how many solutions to the unknown x do I have? In general, I have an infinite number of solutions, right? So how do I pick one in particular? Well, it really depends on what kind of engineering problem you're solving, right? For example, one common solution is to pick the minimum energy solution or the minimum norm solution. So that is written as the following optimization problem. Minimize the 2 norm of x subject to AX is equal to B. So I want to say that of all of these solutions, of all the infinitely many solutions that are available here, find that solution that has the smallest 2 norm. Okay? And this is of interest because large values are something that, in general, we want to try and avoid. And we're going to see more of this, for example, when we get to ridge regression in a couple of lectures. But in control problems, standard usage is to find the minimum norm solution, very commonly applied in different kinds of machine learning settings as well. If you have many solutions, find the smallest one. It's kind of the Occam's razor principle. It's one way of breaking ties. So now we're going to try and solve this using what we just proved in the fundamental theorem of linear algebra. And we're going to try and understand this minimum norm property. Okay? So how are we going to do this? Based on kind of what we've been thinking about so far, let's think about this collectively, right? If I have A times x equal to some B, I have all of this set of solutions. X can be thought of as, the sums of different things, different components. I want to make AX equal to B. Are there some parts of x that might be wasteful in general? Is there something that we've been thinking about that suggests that there might be something wasteful that could be included in x, and we want to remove that to get the minimum norm? Yeah? Components of x that are in the null space of A. So if I have some x, right? So let's say that x satisfies this equation. I know from the fundamental theorem of linear algebra that x can be written as y plus z, where y belongs to the null space of A, and z belongs to the range space of A transpose. Right? So with this, take a minute and see if you can kind of figure out what the solution here is. Take this, take a minute, talk to your neighbor, see where you can get. Talk to both neighbors. Okay, let's work on this together. So if I know that I can decompose x using the fundamental theorem, what does this mean? If I consider a times this y plus this z, what is this equal to? This is a times y plus a times z. What do I know that this is equal to? I know this is equal to b. What is a times y? And this is a times z. This is equal to b. Right? So if x is any solution, what does that mean? The component of x that is in the range space of A transpose is also a solution, right? Would I ever want to choose to place a non-zero component in the null space? Nope. Why is this true? Well, I know that y and z are perpendicular to each other. And so what can I say about the norm of x? The norm of x squared, if I have x is equal to y plus z. What theorem comes to mind? Pythagoras theorem, right? So what can I write this equal to? The norm of y squared plus the norm of z squared, right? So all y is doing is it's adding dead weight to x, right? So I'm always going to choose an x such that the component in the null space is exactly 0, right? So basically I want to now find what is the z component. What is that component in the range space of A transpose? And so if I now consider z is equal to some A transpose W, and I know that A times z is equal to b, this implies that A times A transpose W is equal to b, right? A was an m by n matrix. What is nice about A transpose now? It's a square matrix, right? Is it always going to be invertible? Not really, right? A could be the zero matrix. A could be evil and scheming. But if A has full row rank, then A transpose is going to be invertible. Let's assume that that is the case right now. And I can write W is equal to A transpose inverse times B, which implies that Z is equal to A transpose times A transpose inverse times B, which is our minimum norm solution. So you've seen, this is quite similar in shape and form to the least squares formula, right? It's not quite. Least squares is an A transpose A. There you care about having full column rank. Here you have an A transpose. You care about having full row rank. But these are all ideas that are connected, and we're going to keep exploring how these ideas are connected through the first half of this course. Okay? So start observing these patterns. Yes, question?
How do you know that A transpose has an inverse?
I do not know it in general. I'm assuming for now that A is full row rank, which means that A transpose is invertible. It's a proof worth doing on your homework just to check that, if A transpose is full row rank, that this, if A is full row rank, then this is invertible. But we're not going to do it in class right now.
So is this assumption here just baked into the problem, or is there some reason why A is full rank?
I'm not saying it's full rank. I'm just saying it's full row rank. I'm assuming it for the problem right now.
Okay.
Yeah. But basically, in general, right, here I have fewer rows than columns. So I'm going to care about the row rank here in an underdetermined system. Yes, question?
If we know the range of transpose, can we just take a projection and because we know that x equals y.
Not going to work. Let's talk after class.
Okay.
Yeah. Okay. I'm going to move on to the next topic. So we've done fundamental theorem of linear algebra and optimization problem related to this. Next kind of review-ish topic is we're going to talk a little bit about symmetric matrices. And symmetric matrices are particularly important in this class because a lot of the matrices that end up in optimization problems or in real-world situations that you care about are symmetric. And symmetric matrices have a lot of nice properties. So even if sometimes you don't have a real-world symmetric matrix, you pretend it's symmetric, or you make it symmetric, or you modify it from symmetric, because you want to use the nice properties that exist for these symmetric matrices. So what does it mean for a matrix to be symmetric? A is symmetric if A is equal to A transpose. So are all scalars symmetric matrices? Yes, right? In general, basically you want Aij equal to AjI. So for example, this matrix A, B, B, C is symmetric. We will write this often as A belongs to Sn. So let's just like we say A belongs to Rn by n. Sn is the set of all n by n symmetric matrices. Symmetric matrices are going to be square, right? What's an example? So this will come up in the next lecture when we're talking about principal components analysis, but covariance matrices are symmetric. Basically, actually, any matrix that is of the form BB transpose is going to be a symmetric matrix, right? Because when I take a transpose of this, this is going to be BB transpose, which is going to be B transpose, right? So covariance matrices are a good example. Another example is graph Laplacians. Is the marker still visible, or is it too faint now?
A little bit.
A little bit faint, okay. I will try to get through one more board and then bring out a new one. So what's a graph Laplacian? A graph Laplacian is basically if I have some graph, Aij is equal to 1 if I is connected to j, right? But if I is connected to j, then j is connected to I. So Aij and Aji are always equal, right? This connectivity matrix, which is called the Laplacian, is also a good example of a symmetric matrix. Okay? So why do we care about symmetric matrices? We care about symmetric matrices because they have a lot of nice properties. In particular, their eigenvalues are very nice, and symmetric matrices are matrices that are always diagonalizable. So in general, are matrices always diagonalizable? In general, a matrix need not be diagonalizable, right? So for example, if I consider the matrix 1, 1, 0, 1, this is not a diagonalizable matrix. And just a reminder, what do I mean by diagonalizable matrix? Just if people have forgotten, a matrix A is diagonalizable if I can write it as U lambda U inverse, where lambda is a diagonal matrix. Okay? But when I take this, when I consider this matrix, the property that I want to have for any matrix for it to be diagonalizable is that the algebraic multiplicity, this is a spelling test for me. Algebraic multiplicity of all the eigenvalues is equal to the geometric multiplicity. Whatever, you know what I mean. And what do I mean by algebraic multiplicity and the geometric multiplicity? The algebraic multiplicity is, well, you know, when I find an eigenvalue for a matrix, what am I doing? I'm basically considering this matrix lambda I minus A, right? And I'm using this to generate a characteristic polynomial by considering the determinant of this, right? And I'm finding the roots of that. So the multiplicity of eigenvalue lambda is the number of times lambda appears as a root of this polynomial, okay? So basically, number of times, the multiplicity of lambda is the number of times lambda is a root. Versus the geometric multiplicity is the dimension of the null space of lambda I minus A. So here, when I'm thinking about the corresponding vector space, what is the dimensionality? And let's just see this in this particular example, right? So why don't you guys compute this for me so that it'll save me some time? Compute the eigenvalues, find the characteristic polynomial of this matrix, and find the eigenvalues for me. Right? When I think of lambda I minus A, I get the following matrix. So I have the characteristic polynomial as lambda minus 1 equal to 0. So lambda equal to 1 is a repeated eigenvalue. Right? The multiplicity is equal to 2. Right? Everyone see this? What about the geometric multiplicity? How many people have forgotten how to find a null space? Okay. Everyone who remembers, who didn't raise their hand, teach the person next to you. What is the null space here of lambda I minus A? When lambda is equal to 1, what is this matrix? This is 0, 1, or minus 1, 0, 0. Right? What is the eigenvector corresponding to eigenvalue 0 for this? Anyone? Yeah. 1, 0, right? If I have this times some xy, what is this multiplication equal to? This is always equal to 0. Sorry. This will be negative y, 0, right? Which means that basically everything of the form 0, 1, all multiply, this is an eigenvector. Corresponding to lambda equal to 0. Right? So what is the dimension of the eigenspace that corresponds to eigenvalue 0? Do I have, how many eigenvectors do I have corresponding to this? Exactly 1. What is the dimensionality? 1. Is it equal to the algebraic multiplicity? No. This is not diagonalizable. Okay? Does that make sense? Yes, question? 0, 1 is an eigenvector. This is because you have, basically, if I want to have this be 0, 0, this has to be a 0, right? So any vector where y is a 0 is always going to give you a 0. Come to me in office hours if this is not clear. Has everyone forgotten how to do null spaces? Okay, let's do a quick review of null spaces. What are null spaces? Set of vectors such that you get a 0. So if I want to have any vector such that I get a 0, 0 over here, what do I need to have? If y is 0, what am I always going to get, no matter what x is? Right? So what kind of vectors am I going to have such that this is going to be? So anything where this is 0 is going to be an eigenvector, right? So any 1, 0 is going to be an eigenvector. Right? So it doesn't matter what is here. As long as the second component is 0, I'm set. Yes?
Then why is that eigenvector 0?
Oh, sorry. Typo. Sorry. Okay, good. You haven't forgotten how to do null spaces. I just made a typo. Good. That was a test. Sorry, I typoed it. Okay, does that answer the question? Okay, good. Yeah, I apologize. I miswrote. But this should be 1, 0. Is everyone clear why 1, 0 is an eigenvector? Okay, good. So now you see that in this case, the algebraic and geometric multiplicities are not the same, and therefore, is this matrix symmetric? It is not, right? The off-diagonal elements are not identical to each other. So the nice thing about symmetric matrices is that they are always diagonalizable. Okay? In general, for symmetric matrices, we can write out the spectral theorem. So let A belong to Sn. Then, if A is symmetric, we can say some very nice things. The first is that all lambda I, all eigenvalues, are real numbers. There are no complex eigenvalues. No nicer thing on an exam to see a symmetric matrix and be asked to compute its eigenvalues. You're never going to run into anything complex. Okay? Second, eigenspaces corresponding to distinct eigenvalues for lambda I not equal to lambda j are orthogonal. So if I define, let's say, the space phi I as the null space of lambda I times identity minus A, then phi I is orthogonal to phi j when the eigenvalues are distinct. And the third thing is that if mu I is the multiplicity of the algebraic multiplicity of lambda I, then the dimension of the corresponding null space is equal to mu I. So basically, this is saying that the algebraic and the geometric multiplicities are always equal for symmetric matrices. Okay? So you have real eigenvalues, eigenspaces are orthogonal for distinct eigenvalues, and you have this property of algebraic multiplicity equal to the geometric multiplicity. All of these combined means that you're always diagonalizable. And so in particular, what you can do is you can write for A belonging to Sn, I can write A as some matrix U times lambda times U transpose, where U is an orthonormal matrix and lambda is diagonal. And here I actually mean diagonal. No typo. Remember, orthonormal matrices are matrices such that all of the columns are orthogonal to each other and they're normalized, so their norm is 1 for every single column. Orthonormal matrices have the very nice property, it's a good homework problem to do, that U transpose is always equal to identity. So the transposes are inverses. This is a nice property of orthonormal matrices, okay? If this isn't something that you've seen before, definitely worth just doing the quick exercise to verify this at home, okay? But this is the nice diagonalization that we have thanks to the spectral theorem for symmetric matrices. I'm not going to prove all of this here in class today. 2 is going to be on your homework, and we're going to discuss 3 in class today because that's the hardest one of the 3. So we're going to prove property 3. 1 and 2, I don't know if we'll put 1 on your homework, but we might. So it's something to check. Question? Here, why is lambda 0? Sorry, again, another typo. This is corresponding to lambda equal to 1. Okay, so we're going to show why 3 is true. And to do 3, we're going to first prove a lemma. And here we're going to say let lambda comma u be an eigenpair for A. Then there exists orthonormal u such that U transpose A U is lambda, and then zeros here, zeros here. Maybe that's confusing. And a B here. And B is symmetric. So what is this lemma saying? I'm saying that if lambda is an eigenvalue and u is the corresponding eigenvector, then I can find an orthonormal decomposition of A such that U transpose AU is such that this lambda shows up in the first entry, but the rest of the row and this column is all zeros, and what is left here is a symmetric matrix. Okay? And why do I want to prove this lemma, right? How is this lemma going to help us kind of pick out these multiplicities? What am I trying to do here? So the strategy that we're going to use for proving 3 is going to be an induction-based strategy or a unraveling-based strategy. So what I'm going to do is I'm going to show that A can be related to this matrix B, where B is also symmetric, but B is lower dimensional, right? And now if I can say something about the eigenvalues of this lower dimensional thing, I can count the eigenvalues of the lower dimensional thing, and I know if I can relate the eigenvalues of B and A, then I can kind of say that, well, if I add this one more eigenvalue, then I can say that, well, I'm just adding one more, right? So basically, once we have this lemma, we can say that, well, if the algebraic multiplicity and geometric multiplicity are the same, are equal for B, lambda, I can count the multiplicity of lambda. Either it belongs to B, in which case I'm increasing it by 1, but I'm also increasing the dimension by 1. Or it's not an eigenvalue for B, in which case it has just algebraic and geometric multiplicity 1 itself. Right? So basically, by having this decomposition, I'm setting myself up for an induction-based proof. Okay? Does everyone see that we're trying to decompose the problem into this smaller thing? Yeah? Good. So why don't you try to prove this while I'm erasing these boards? Okay. We don't have that much time, so let's try and get through this, okay? So we're going to do this proof by construction. And what we're going to say is we're going to say consider the following U. So what do I want to show? I want to try to pull out a lambda, right? And I want to have something multiplies A, or A multiplies something and I get a lambda. So what is the vector that I have? What do I have? I don't have that much, right? So when I'm going to try and construct this U, what am I going to put as its first column? I want it so that A multiplies this U and like I get a lambda and a bunch of zeros. What do I want to have? I want to start with what I'm given, right? Right, if I take A times U and then some other stuff, what am I going to get? I'm going to get a lambda out, right? So if I consider the following U, which is this U vector followed by something, how am I going to get the rest of this U, this U1? What is something what do I want to be true of U? I want it to be orthonormal. I'm given one vector. What tools do we have? Gram-Schmidt, we don't have that much, right? So what are we going to do to fill out the rest of this matrix? We're going to do Gram-Schmidt, right? So we're going to use Gram-Schmidt to fill out a basis such that this is now an orthonormal vector, or orthonormal matrix, right? So I have U times this, and now let me consider U transpose AU. What does this look like? U transpose is basically this U here transpose U1. Then I have an A matrix. And here I have this U1, or not U1. Let me make these. Okay? So now when I have this, if I think about A times this thing, right? When I make A, this is a matrix A, and this is a bunch of column vectors. So what is this going to be equal to? I have this matrix here the same. A times this is going to give me basically the first column here is going to be A times U. And then I'm going to have A times U1, right? Just doing matrix vector multiplication, nothing fancy. And now here, when I do this next multiplication, I have this U here. So when I do here, I'm going to go row by row. When I take this row times this column, what am I going to get out? What is this AU? What can I rewrite this as? This thing is just lambda U, right? This column, I know exactly what it is because U is an eigenvector. So then I have U times lambda times U. What is that going to give me? So I'm just going to get this lambda out. This is going to be equal to this first entry. It's just going to be a lambda here because U is a normalized eigenvector, right? So the norm of U is just going to be 1. And now, because of Gram-Schmidt, what is the property of U times A times U1? When I take U times A times U1, I'm basically going to get all of these things going to be zeros. All of these things are going to be zeros, and I'm going to get a B here. And what is this B going to be? This B is going to be U1 transpose B is going to be U1 transpose, maybe I shouldn't write it like this. I should write it as but by its very structure, what is true of B? Right? B transpose is just going to be exactly equal to B. Right? Because I'm going to get B transpose is equal to this whole thing transpose. These are going to flip. A is already symmetric. A is equal to A transpose. Right? So B is equal to B transpose. So B is symmetric. Does everyone see this? By using Gram-Schmidt, we basically have exactly extracted this structure out. Yeah? The question is, why is the top row zeros? So this is just block matrix multiplication, right? So I'm going to have U transpose times this row times this column is going to give me this lambda. This row times the next column is going to give me a 0 because of orthonormality. Because A is symmetric, I have A is equal to A transpose. So U transpose times A is equal to U transpose times A transpose. And this is going to be equal to AU whole transpose, which is going to be equal to lambda U. Now, when I multiply this by U1, I have orthonormality, so I'm going to get all of zeros, right? So you're basically using the fact that U is orthogonal to every single column here to be able to get this row of zeros and this row of zeros. Okay? And you're using the fact that A is symmetric. Okay, I only have a couple of minutes, so I want to kind of walk you through the remainder of the induction proof. What should I erase? I guess. I don't have enough time to do it all out, but I'll try to give you the basic idea, right? So I know that basically this decomposition is true. So now let's say that algebraic multiplicity and geometric multiplicity are equal for all B's that are one dimension smaller, so that are belonging to Sn minus 1, right? This means I can write B as a diagonalized matrix. So I can write B is equal to some V transpose times some lambda matrix times V, where this guy is diagonal and this guy is orthonormal. And remember, these are all now belonging to our n minus 1 by n minus 1, right? These are n minus 1 dimensional matrices. So I don't have time to kind of walk you through the intuition for this, but I know now that U transpose A U is equal to lambda, this row of zeros, this row of zeros, and this B. So now if I considered V times U transpose times A times U times V transpose, what I would get is this entry would not be affected. I would still get a lambda here. And what I would get would be V B V transpose. Yep. And because I know of this decomposition, I know this thing is just now this matrix lambda. So this is equal to this little lambda, zeros, zeros, and this big lambda. So all we're doing is using properties of block matrix multiplication. If this is something that is a little bit confusing, go and work it out. But basically what you're going to see is that you will be able to get this exact decomposition out. Okay? So sorry, it's a quick proof. This is the key idea. And let me know if you have questions. For constructing these V's, you're going to have to augment them with a vector, but hopefully that part is clear. Sorry for the last rushed end. Thank you.